Okay, Model 1 was a reasonably a good model. Let's see if we can further improve the fit by adding other regressors. We saw from our scatter plot matrix, income also has a strong positive correlation with prestige. Now we try to model prestige using education and income. Now we have two regressors. So this is a multiple linear regression model. This is how you should fit a multiple linear regression model. You can use the same function LM. Here you need to pass your y variable, then tilde mark, and next you have to pass your regressors. They should be connected through using plus sign. Here you have to specify the data set you're gonna use to build the model. You can use the summary function to get the output. In multiple linear regression analysis, F statistics, this one, becomes more important as this statistic is testing to see if at least one of the coefficients is non-zero. When there is no relationship between the response and the predictors, we expect the F statistic to take on value close to 1. In this case, p-value of F statistic suggests that at least one of income or education must be related to prestige. However, this does not necessarily imply that the relationship found is an appropriate one for predicting prestige score. Further tests of model adequacy are required. The adjusted R-squared value is 79%. Earlier it was 74%. The adjusted R-squared increases only if the new term improves the model more than that would be expected by chance. Now let's do the residual analysis of this new model. For that, we need to calculate residuals and the fitted values. So in order to calculate fitted values and residuals and the other observation-based values, we can use the augment command, augment function in the Broom package. One advantage of this data frame is you have everything stored in one data frame. All variables, all model-based statistics, in order to use ggplot, you need to have all variables in a single data frame. Now you can use ggplot to draw any kind of graphs using the variables available here. This is residuals versus fitted value. It seems like constant variance assumption is violated. Because we have inward funnel shape. So we have to modify the model and refit it. The normality assumption is satisfied. In the QQ plot, y-axis is ordered standardized residuals. On the x-axis is the ordered theoretical residuals. This is the expected residuals if the errors are normally distributed. If our errors are normally distributed, these points should fall roughly on a diagonal line. From the results of Shapiro-Wilk tests, also we can see the errors are normally distribution. Assumption is satisfied. It is important to plot the residuals versus every available variable to ensure that a candidate model is the best model possible. Plot of residuals versus education doesn't show a systematic pattern, but plot of residuals versus income shows a systematic pattern like this. If a plot of residuals versus another variable did show systematic structure, the form of model with respect to that variable would need to be changed. So now we are going to refit the model. Now instead of income, I use log transformation of the income variable.